Hi all. Today we will discuss about relations and functions, which is the first chapter of class 12 N.C.E.R.T textbook. Here it is the part 2 video. Composition of functions and invertible functions. Here you can see three circles. Circle 1 indicates students of class 12 and circle 2 indicates the roll number of class 12 and circle 3 indicates the secret code. You know that the roll number of students will be changed to secret code during the evaluation process in the public examination. Here, assume that the roll number of student S1 is 111201 and secret code of this roll number 111201 is 501. Like, assume that the roll number of student S2 is 111202 and the secret code of this roll number is 502. Similarly, the roll number of S3 is 111203 and the secret code of this roll number 111203 is 503. Similarly, for S4 and S5. That is, there exists a function f from this student set to roll number set. Like f of S1 is 111201. F of S2 is 111202. F of S3 is 111203. S4 is 111204. S5 111205. And there exists a function g from roll number set to secret code set. That is, g of 111201 is 501. G of 111202 is 502. G of 111203 is 503. Like for these two numbers also. That is, there exists a function f from student set to roll number set and there exists a function g from roll number set to secret code. Here, the secret code of S1 is 501. How? The roll number of student S1 is 111201 and this number changed to 501. Hence, the secret code of S1 is 501. Similarly, the secret code of S2 is 502. There exists an arrow from S2 to this number and an arrow from this number to 502. Hence, the secret code of student S2 is 502. Similarly, what is the secret code of student S5? Yes, it is 505. That is the composition of f and g. F is a function from student set to roll number set and g is a function from roll number set to secret code and g of f is a function from student set to secret code. I think now you get an idea about composition of functions. Here is the definition of composition of functions. Let f from a to b be a function and g from b to c be another function. Then the composition of f and g, denoted by g of f, is defined as the function g of f is a function from a to c is given by g of f of x equal to g of f of x for all x in a. Here, x is an element in the first set A. F of x is an element in the second set B. And G of f of x is the element in the third set. That is, there exists a function f from a to b. That is, f of x is present in the second set. And there exists a function g from b to c. Here, the elements are like f of x. Then, g is a function g from b to c. So, the elements in third set is like g of f of x. Here, f is from a to b, g is from b to c, and g of f, composition of f and g, is from a to c. That is, x is mapped to g of f of x by the function g of f, composition of function. I think now you are clear that what is composition of function. Here is an example. Then it will be more clear to you. Here, f is a function from the first set, which consists of the elements 2, 3, 4, 5, to the second set, which consists of the element 3, 4, 5, 9. And g is a function from this set to this set. Here, the yellow colored set consists of the numbers 3, 4, 5, 9, which is the domain of the function g. And the last set consists of the element 7, 11, 15, which is the range of the function g. Here, f of 2, that is 2 is mapped to 3 and 3 is mapped to 4, 4, 5 are mapped to 5 in the second set. That is, f of 2 is 3, f of 3 is 4, f of 4 and f of 5 are 5. Here, the mapping of G is like this. 3 and 4 is mapped to 7. 5 and 9 is mapped to 11. Now, what is the task? Find G of f. That is, we need to find the function g of f. Here f is from this set to this and g is from this set to this. Then g of f is from this green colored set to this red colored set. Now, what is g of f of 2? 2 is mapped to 3, 3 is mapped to 7, hence 2 is mapped to 7. Or by the definition, g of f of 2 equal to g of f of 2. What is f of 2? 3. Hence, g of 3. What is g of 3? It is given that 7. Hence, g of f of 2 equal to g of f of 2 equal to g of 3 equal to 7. Hence, the composition function g of f maps 2 to 7. Similarly, g of f of 3 equal to g of f of 3. What is f of 3? 4. Hence, g of 4, which is equal to 7. Hence, the composition function g of f maps 3 to 7. Now, what is g of f of 4? G of f of 4 equal to g of f of 4. What is f of 4? F of 4 is 5. That is, 4 is mapped to 5. Then 5 is mapped to 11. Hence, G of f of 4 is 11. G of f of 4 equal to G of 5 equal to 11. Similarly, G of f of 5 is also 11. Hence, G of f gof is a function from this green colored set to this red colored set, and the function is G of f of 2 is 7, G of f of 3 is 7, G of f of 4 is 11, G of f of 5 is also 11. So G of f is clear to you. Here is the definition of identity function. Let M be a set and let F be a function from M to M. That is, here domain and codomain are same. Then F is said to be an identity function if F maps every element itself. Here S1 maps to S1, S2 maps to S2. Similarly, for all elements, the mapping is to itself, the same element. Here, F is said to be identity function. I think now you are clear about identity function. Here is another example of composition of functions. Let f be a function from set of all real numbers except 7 by 5 to set of all real numbers except 3 by 5, and f of x is defined as 3x plus 4 by 5x minus 7, and let g be another function from set of all real numbers except 3 by 5 to set of all real numbers except 7 by 5, and g is defined as g of x equal to 7x plus 4 by 5x minus 3. Here our task is we need to find f composition g, g composition f, and we also need to find, or we also need to show that f of g equal to identity and g of f is also an identity function. Here the domain of this function is, or the domain of f composition g is A, where A is the set of all real numbers except 3 by 5, and the domain of the function g of f is B, where B is the set of all real numbers except 7 by 5. Why we delete 7 by 5 and 3 by 5 from this domain and codomain sets? Here, when we put x equal to 7 by 5, that is, assume that 7 by 5 is also included in the domain, then f of 7 by 5 equal to, now in the case of denominator, 5 into, instead of x we will put 7 by 5. 5 into 7 by 5 minus 7. 5 will be cancelled. Then 7 minus 7 equal to 0. That is, when we put x in instead of x 7 by 5, then f of 7 by 5 equal to, here denominator becomes 0. Which, to avoid this situation, we eliminate 7 by 5 from the domain. Similarly, for the 3 by 5, we will not get 3 by 5 as the image in the codomain set. Hence, we eliminate 3 by 5. The same case in the function g also. So, the domain and codomain are like this. I think now the question is clear to you. So, our task is we need to find composition of f and g, composition of g and f, and we need to prove that both are equal to identity function. Now, we can move to our first task. First, we will prove that, or we will find composition g of f of x, and we will prove g of equal to IB, or identity function on the set B. What is g of f of x? G of f of x equal to, instead of f of x, we can write the definition 3x plus 4 by 5x minus 7. So it's written here. Now when we substitute, instead of x, we will write this big number. So it is 7 into, instead of x, we will put 3x plus 4 by 5x minus 7. Then 7x plus 4 by 5x minus 3. Here we will apply cross multiplication and cancellation. That is, we will calculate 7 into 3x plus 4 into 1 plus 4 into 5x minus 7 divided by 5x minus 7. Here also 5 into 3x plus 4 into 1 minus 3 into 5x minus 7 divided by 5x minus 7. Both numerator and denominator 5x minus 7 is present. So we can cancel it. Also we can cancel 28 and minus 28. Then we get the answer like this. Similarly, here also we can find f of g of x. First we find g of f of x. Here we will find f of g of x. What is f of g of x? F of, here instead of g of x, we can put the definition of g of x. F of 7x plus 4 by 5x minus 3. Here 3x plus 4 by 5x minus 7 is the definition of f. So instead of x, we put this big number. Hence f of 7x plus 4 by 5x minus 3 equal to 3 into that big number plus 4 by 5 into that big number minus 7. Again, by cross multiplication and cancellation, we get the result like this. Here 41x by 41, 41 cancelled. Hence, we get the result as x. Here also, we got f of g of x equal to x for all x in the domain of the function f of g. That is, fork and gof. Both are identity functions. I think now you are clear about the identity function and composition function. Here, another question. Show that if f is a function from a to b and g is a function from b to c, both are 1, 1, then we need to prove that their composition g of f or gof from a to c is also a 1, 1 function. Moving on to the proof. Suppose g of f of x1 equal to g of f of x2. I think you know how to prove a function is 1, 1. How? To prove a function f 1, 1, first we assume that f of x1 equal to f of x2 for all x1, x2 in the domain of f. Then we need to prove that both numbers x1 and x2 are same. That is, if f maps x1 and x2 to to the same image, then that x1 and x2 should be same. Same in the same case, here our task is to prove that g of f of x is 1, 1. For that, we took 2 points x1 and x2 from the domain of g of f. And we assume that g of f of x1 equal to g of f of x2. Now our task is to prove that these 2 points x1 and x2 are same, or we need to prove that x1 equal to x2. Now what is g of f of x1? G of f of x1 equal to, instead of this, g of f of x2. But we know that g is a 1, 1 function. It is given in the question. Also, g of a point equal to g of another point implies that these 2 points are same by the definition of 1, 1 function. Hence, f of x1 equal to f of x2. But we know that f is also a 1, 1 function. Hence, f of x1 equal to f of x2 implies that x1 equal to x2. Why? F is a 1, 1 function. That is, from the beginning, we assume that g of f of x1 equal to g of f of x2. At last, we got x1 equal to x2. Hence, g of f is a 1, 1 function. Hence, here f is a function from a to b, b is a function from b to c, then their composition g of f is also a 1, 1 function. Given that f and g are 1, 1 function. That is, composition of 1, 1 function is also a 1, 1 function. Here is the definition of invertible function. A function f from x to y is defined to be invertible if there exists a function g from y to x such that G composition f and f composition g are identity functions. That is, a function f is given, we need to find another function g from y to x which satisfies these two conditions. Then we can say that this f is an invertible function and g is the inverse of f. Here is one remark or very important point. If f is invertible, then f must be 1, 1 and onto. Also, if f is 1, 1 and onto, then f must be invertible. That is, f is invertible if and only if f is 1, 1 and onto. Here is another example or another question. Let f from natural numbers n to y be a function defined as f of x equal to 4x plus 3. Here, y be the set of all y in n such that y equal to 4x plus 3 for some x in n. That is, y consists of all the numbers 4x plus 3 where x is in the domain of f. We need to prove that f is invertible and we need to find the inverse of f. For that, consider an element y of y. Here, a function f is given. We need to find f is invertible and we need to find the inverse of f. By the definition, we need to find another function g from y to n such that f composition g and g composition f both are 1, 1. For that, y is an element from the set y. By the definition, it's given that y should be like 4x plus 3 for some x in the domain n. That is, if we take any number y from the codomain y, then that y should be in this form, 4x plus 3 for some x in n. Then, by just simple calculations, y minus 3 equal to 4x. That is, we just take 3 to this left side. Then we just interchange RHS and LHS. We got 4x equal to y minus 3. Then we just move 4 from LHS to RHS. That is, we get x equal to y minus 3 by 4. Or we can define another function g from y to n by g of y equal to y minus 3 by 4. Now, in the same method, we will find g composition f and f composition g. Then we will prove both are identity function. Hence, we can prove that f is invertible. For g of f of x equal to g of f of x, which is equal to, here f of x it's given like 4x plus 3. So, we substitute 4x plus 3 instead of y. Then we get like this x, that is g of f of x equal to x for all x in the domain of g of f, which means that g of f is a 1-1 function. Similarly, we will find f of g. Here also, by simple calculation, we get y. That is, f of g of y equal to y for all y in the domain of f of g, which means that f of g is also an identity function. That is, we got a function g from y to n such that g of f and f of g are identity functions. Hence, we can prove that f is invertible. The inverse of f is y minus 3 by 4. Here, 2 exercises are for you. Just read the questions and try to answer it. Here is the end of chapter 1, Relations and Functions of the textbook N.C.E.R.T. class 12. Thank you all.